My name is George Phillips. I'm proud to be a part of this phase retrieval workshop. Sorry I can't be there. I'm going to be on a plane when you're watching this, but I was asked to give a brief introduction to direct methods and to molecular replacement, which I'm very happy to do. It'll be a very basic level, but I hope it will help set the tone for more sophisticated and modern phase retrieval methods. So let me share my screen. So like I said, I'm going to talk a little bit about direct methods. Hopman and Carl got a Nobel Prize for figuring this out about 50, 60 years ago. It's extremely useful for small molecule crystallography, for cases where you have small chemical structures that diffract to high resolution. I'll explain why that is and how it might relate to protein crystallography. And then I'll give a brief introduction to molecular replacement and how that works. Now, let me start with a reminder of the crystallographic electron density equation. Rho here, which is commonly used for density, represents the electron density. It's a function of three variables, x, y, and z, sometimes denoted by a vector x. That's why it's bold. And you can calculate this electron density from this Fourier summation if you know the complex structure factors that come from the Fourier transform of the density. Then you can do this inverse Fourier transform to recover the density. And we talk about the phase problem, and that's because this f of h is a complex number, and we don't know how much of that number is real and how much is imaginary. A phase is often described as the imaginary part over the real part, which is an angle. The tangent of that is the angle whose tangent is that is the phase angle. So you either have to know the phase angle or how much is real and how much is complex to complete this summation. And again, H is bold. This is sometimes HKL, an integer triple, and X is XYZ, also an integer triple. So that this is the dot product of H, and X. Going the other way, you can get from the location of atoms, here described as x of j for the jth dotted with h, e to the 2 pi I h dot x times some term that represents the scattering strength of the atom, and that gives rise to this complex structure factor. And here it is in the expanded term, just showing the dot product written out as a series of components, and you sum over all the atoms in the unit cell. So how do you get these phases directly? I mean, this has been a challenge of crystallography from the beginning. It's a very difficult problem, but people have made headway making a few assumptions, including the assumption of point atoms. So if you were to assume that atoms were points in a sea of vacuum, then you can make some relationships that help determine the phases. The key components here are called triplet phase relationships and the tangent formula, which I will describe briefly. So the key points in these kinds of direct methods are that you have a sparse set of point-like identical atoms in a vacuum. Why do they have to be identical? Well, it simplifies the equations and lets you do some algebraic manipulations that lead to phase relationship. But basically, if I had to give 4 words for how direct methods work, is that electron density piles up where the atoms are, right? They're not random. They pile up to reinforce these point-like atoms, if in fact that's what your structure is like. And if you get into the literature, you'll start to read about some structure factor that are modified. So if you have your magnitude of FH, again, this capital H is an integer triple, F for a particular spot, HKL, that magnitude we can measure from a diffraction experiment by taking the square root of the measured intensity. So we know the magnitudes of FHs, but not the phases. These are often converted to what are called E's or U's. E's are modified by all the reflections at the same resolution. This tends to remove effects of the scattering factor or the B factor. You can also normalize by the number of electrons, or people sometimes work with U's, which are normalized by the total scattering, which is so that every structure factor amplitude winds up in a range 0 to 1. And you'll see for special purposes the use of E's and U's instead of magnitude of FH. So what are some of the key relations that come from this assumption of point-like atoms? There's the so-called sigma-1 relation that I'll talk about. You may have heard about the Sayre equation, which leads to something called the triplet relation. And there's also there are also phase relationships that are called quartets because they use 4 instead of 3. There are positive and negative quartets that you can that I'll briefly mention. You can have higher order quintet relationships and so on. And in the end, something called the tangent formula was developed, which allows one to propagate estimated phases to phase other reflections, even starting with random phases. The tangent formula can help produce a solvable structure. So let me say a few words about the sigma-1 relation. So on the assumption that you have 2 measured factor amplitudes that have been normalized, if E sub H and E sub 2H, meaning you multiply the H, the K, and the L values by 2, if these are both large, the phase of E 2H is likely 0. And I'd like to explain why that is true. It turns out it doesn't matter what the phase of EH is for E2H phase to be 0. So the graphs I'm showing are from this International Union of Crystallography monograph, which I encourage you to read to see a little more explanation and a little more detail on some of the things that I'm talking about today. But let's move to this two-dimensional case, two-dimensional crystals, say. Here's an outline of the unit cell. And you can imagine the let's call it the 1, 1, 0 reflection. Let's say we're looking down the C-axis, the 1, 1, 0 reflection. Let's say it has a phase of 0. So it would be a sine wave that's very positive here, very negative here, comes back to being very positive here. It would go up, down, up, and because of the squaring of the structure factor, you would get a row of high density where atoms are likely to be at this position, and this position. Okay, so the atoms, if the 1, 1, 0 is large, then the stripes in these positions would tend to be large. And now if we want to look at the E2H, which would be the 220, it could have a phase of 0 or pi in this particular case. And if the phase were negative, it would start at 0. Sorry, if the phase were pi, it would start at 0. If the phase were if the phase are 0, it's high at 0. If the phase were pi, it starts not on 0. But the key point is that it's much more likely if the 2, 2, 0 spot piles on to the 1, 1, 0 spot. So if this is if that other phase of E sub h is big here and here, because atoms pile up, it's much more likely that the phase of the 2, 2, 0 will pile its density on top of the 1, 1, 0, which corresponds to a phase of 0 and a large value here instead of some other phase as shown here. So if they're both large, they both probably reinforce atoms in the same place. And so this leads to the likelihood of the phase for the E2H to be 0. And if you think of, instead of looking at this diagram, if you make a little plot, you can see why it doesn't really matter what the phase of EH is. If they're both large, the phase of E2H is likely 0. Because the electron density wave that would be maximally reinforced when the phase of 2H is 0, even if the initial one had a phase that was negative. Okay, so let's talk a little bit about the Sayre equation and the triplet relationship. So I'm not going to go through this whole derivation, but you can see that there's a relationship between the phase or the structure factor amplitude of the H reflection relative to K and the H minus K reflection. And again, this has to do with density always piling up in the same place. And I encourage you to look at this slide if you want to see how the derivation of this relationship comes from the pairing. Point-like atoms, it wouldn't matter if you squared the density or it was the same density. So this squaring becomes an important factor in the development of the Sayre equation. And this triplet relationship, this triple H, K, and H minus K, take on phase relationships under the assumptions, which means that the phase of the minus H reflection, the phase of the K reflection, and the phase of the H minus K reflection all add to be 0. Here means, here the wavy lines don't mean approximately 0, they mean most likely 0. Okay, and this is true when this is more true, the magnitude, when the magnitudes of these reflections are all large. So this again is just the piling on phenomena in 2 dimensions, and the quartet relationship is this same piling on idea in 3 dimensions. So this has a relationship between the phase of the H, the phase of the K, and now a third one, a third integer triple. Now, don't confuse these with the integer HKLs defining a single lattice. This is an HKL, this is a different HKL, and this is a different HKL, but they happen to use the same letters. But these capital ones each refer to a distinct integer triple. The phase of the H, the K, the L, and the minus H minus K minus L reflection can be shown again to be 0 when E4, which is the product of these 4 E's, is large. So again, piling up in one area of the density map that is the driving relationship. And this Hopman and Carl further derived an expression for phase relationships called the tangent formula, which is very useful in propagating these concepts to the whole set of phases. So if you are comparing the relationship of phases for the K, the HK, H minus K, if you sum up all of the structure factors for K, H minus K, if E3 is large, then this formula is likely to be true. And you can actually predict the phase of the H reflection given the K and the H minus K reflections. And so the way this plays out, again, if you have point atoms in a vacuum, you can start with random phases. You may or may not know that you can get freely assignable origin defining phases. And so usually you can pick 2, 3 phases that only set the origin for your particular space group. And then you start applying this formula to expand out an initial set of random phases, correcting them by the tangent formula. The very strong structure factor amplitudes will tend to drive this set to a more accurate set of phases than the random ones. It goes to some convergence. When it converges, you make a Fourier map and hope your atoms come into view. And this form of phase retrieval works amazingly well. It's been refined statistically since then, but this is the basis of direct methods. There's a very sophisticated piece of software called shellxd, and I encourage you to read about shellxd in the notes from this workshop a number of years ago, but that describes more detailed how it works. For me to explain it, I need to be sure that everybody knows what a Patterson function is. A Patterson function is this autocorrelation function, which is the convolution of the electron density map as a function of X, Y, and Z with its inverse. So there's a plus sign here. It's that this autocorrelation function gives this capital P, which is the Patterson map. And you can calculate the Patterson map directly from amplitudes. You don't need any phases. So f of h squared, the magnitude of the structure factor squared, which is Fourier transformed, gives this Patterson map. And so U is a XY, is like an XYZ value, but in this interatomic distance space. And there's something called the convolution theorem, which explains why this squaring is equal to this convolution, and vice versa. That's a very useful way for crystallographers to go very easily back from real to reciprocal space when you need a simple multiplicative function. So let me illustrate an example Patterson map. So say you have a unit cell like this, and this is your simple molecule. The Patterson map will consist of all the interatomic vectors. Because this is a convolution, it's like putting each of these atoms at the origin and then adding where the peaks are in space for each movement of this object all around. Because it's zero except at these points, you move each of these points to the origin and plot where the dots fall. There are lots of peaks at the origin because every atom falls on itself there. What we wind up with is a set of peaks in Patterson space that are sort of ghosty images of your actual molecule. And these nice illustrations, I should say, came from a protein crystallography course that Randy Reed has put online. So the shellxd uses Patterson methods as well as the triplet and relationships that I described below to try to get phases. And this is particularly useful in determining substructures. For protein crystallography, it's particularly useful in determining substructures. And what do I mean substructure? Well, if you've soaked in a heavy atom, or maybe you have a bunch of sulfurs, you have some that are much heavier than the others. And this is sort of reminiscent of the direct methods that I talked about. You have a sparsely populated unit cell of heavy atoms. The carbon, nitrogen, and oxygen are kind of like noise. So this means direct methods combined with some Patterson methods allow shellxd for protein crystallography to find where all the heavy atoms are. And that's incredibly useful. This is an important phase retrieval process for finding the heavy atoms in macromolecular crystallography. The flow for shellxd looks like something like this. You start with some random atoms, or maybe better, some atoms consistent with the Patterson. Maybe they're not exactly right, but at least they're consistent with the Patterson. So you have this real space location of trial atoms. You calculate this you calculate the phases and the structure factors from this set of atoms in reciprocal space. You refine the phases using the direct methods that I described before, and you go back and make a new map. And if this has converged, yes, you're done. If this is no, you go back around, you take these atoms, you again maybe pick a few more or adjust them to be consistent with the Patterson, and you go around and around again. You can go go around a few hundred times, and you can look at essentially R-free or some correlation between your observed and calculated normalized structure factor amplitudes. And when you get a good fit, you're done. And this shellxd works amazingly well. It works for small molecule crystallography, and it works for finding the substructure in macromolecular crystallography. So when do direct methods work? With high resolution data. That is, if you have atomicity and the atoms are point-like. If you have not too many atoms, maybe up to 1,000, proteins only works for proteins if you have very high resolution, sort of near atomic resolution, and not too big. But it's really good for working to directly determine heavy atom substructures within a protein crystal. That's my spiel on direct methods, and I'm going to start a video related to molecular replacement.